to say thank you so much to my latest Patreon members, Afshan Ismet and Michael Hirsch. If you like these videos, please join them in supporting me on Patreon. Thank you.
So now we're going to go over some additional properties that are implied by the field axioms. So first, we're going to prove some additional laws implied by the addition axioms. And then after this, we'll do multiplication, and then we'll do some that are implied by both of them together. But so the axiom for addition imply the following, which we'll prove in a second. That if x plus y equals x plus z, then y equals z. Again, this stuff's obvious. This is the foundation of our first classes in algebra, right? This is what you do. If you have the y equals z, you can add the same thing to both sides, and you'll end up. Actually, I guess this says the opposite. That if you have this, that shows that you have that. That shows that y plus z or y equals z. Y equals z. And then, as I actually just said a minute ago, if x plus y equals x, then y must equal 0. C is that if x plus y equals 0, then y equals the inverse of x. And D is that the opposite of x equals x. So again, every one of these is obvious, but they're actually not required for your set to be a field, because you can deduce all of these from the field properties that we have defined. So A is the cancellation law, which is what I said in basic algebra. When you're trying to solve an algebra problem, if you need to move something from one side to the other, you just add the same thing to both sides, and you end up with something they're still the same. So that's the cancellation law. Write that down. Does it have two L's? Yeah. Part B asserts that there's only one zero. This is what I said before too. In the field axioms, we say that there is an element where if you add x to that element, you get x. This says that in fact there can be only one in a field. There's only one zero. And C says the same thing for inverses. So this is like A4, that there's only one zero. And this says that there's only one inverse for each one. So if x plus something is 0, there's only going to be one number that you can add to a number to get 0. 5 plus minus 5 is 0. You can't add anything else to 5 to get 0. So, okay, so let's go through these real quick and prove them. So A. So if we're given that x plus y equals x plus z, then we can use that. Let's just go through a series of equalities here. So we have y equals 0 plus y, right? Because we can add 0 to anything and we get the same number. And then we can replace that with minus x plus y. This is going to equal the same thing because minus x plus x is 0. Use associativity to have minus x plus y. And then we started with an assumption is that this equals minus x plus z. And then use associativity again. We have minus x plus z. Minus x plus x is 0. So we started with y. Going through the assumption, we end up with y equals z, which is what we were trying to prove. Whoops. Which is what we were trying to prove. So that proves A. A was that if you have start with x plus y plus x equals x plus z, you can prove that y equals z. So again, it's interesting because this is such a fundamental property, but we can actually deduce it from our rules. We don't need to assert it as an axiom. So let's do the same thing for the remaining ones. So for B, actually, I'm going to rip out this page so we can refer to it. Okay, so B is that if we have x plus y equals x, then y is 0. So if we just if we start with A and we let the z here equal 0, then x plus y equals x plus 0, which implies that y equals 0. So we were trying to prove that x plus y equals x, then y equals 0. So if we just use A and we let z equal 0, then we have that x plus y equals x means that y equals 0. Did that make sense? So we're trying to prove that x plus y equals x shows that y equals 0. So we're just going to use A. So we have x plus y equals x plus z, and rule A shows then that y has to be the z, which is 0. Okay. For C, let z equal minus x in A. So we use the same rule once again, but this time we let z equal minus A. So then we have that x plus y equals x plus minus x. And that implies again that y equals minus x, which is just what we were looking for. Right? Y equals minus x. And finally for D, so let's do C again. So for D, we're trying to prove that minus x equals x. And again, I know I've said this 10 times, but I just think it's very interesting that this is actually not an axiom of the field. It's something that we can conclude simply from an inverse law, an identity law, associativity law, and so on. So starting with C, let's start with minus x instead of x. So we have here, here minus x plus y equals 0. So in C, the rule of C is that if you have x plus y equals 0, then y is the opposite of x. So here we have minus x plus y equals 0. That means that y is going to be the opposite of x. Now we know from the inverse property of fields that minus x plus x equals 0, but we just showed here that y equals minus x. So we must have that minus x equals x. Which is what we're supposed to show. Okay? Cool. Okay, so now, very similar laws for multiplication. Okay, so additional laws. Implied by multiplication axioms. So they are very similar. We have A, but with one big difference. Always if x does not equal 0 and xy equals xz, then y equals z. B, if x does not equal 0 and xy equals x, then y equals 1. C, if x does not equal 0 and xy equals 1, then y equals 1 over x. And D, if x does not equal 0, and, oh no, then, so how do we do this? In the other one we had minus x, right? So it's 1 over x equals x. Okay, so to prove these quickly, we do it virtually the same way, which shows you how similar the multiplication axioms are to the addition axioms. The two operations they're isomorphic. The only difference is that you can't divide by 0. But I'm not going to go into more detail about why that is, but you can see from the similarities here that they're very, very closely related. So the same thing, if we have that if we start with xy equals xz, and x does not equal 0, then we start with y equals 1 times y. That's identity. And then 1y we can rewrite as 1 over x times y, which is the inverse, right? Because 1 over x times x is 1. Associativity, we have 1 over x times xy. We started with the assumption that xy equals xz, so 1 over x. So this equals 1 over x times xz. Apply associativity again, and we have 1 over x times z. 1 over x times x is 1, so we have 1z equals z. So using this piece right here is the assumption. Using that in all of our axioms, identity, inverse, associativity, and then associativity, inverse, and identity, we have that y equals z. Okay, that's A. So for B, if we let z equal 1 in A, oh, actually, I'm going to take this sheet again so we can look at it. So if we let z equal 1 in A, then we have that xy equals x1, which implies that y equals 1. And that was exactly what we wanted to show. If xy equals x, then y equals 1. So that was easy. C. If we take z equal 1 over x and plug it into A, then we have, again, xy equals x times which equals 1. Right, so what we're trying to prove is that if xy equals 1, then y equals 1. And from A, that's what we have. We have xy equals xz, then y equals z. Is that what I'm trying? Yeah, then, oh, I'm sorry, we're doing this one. Then y right? So we went back to A, we let z equal 1 over x. So then xy, if xy equals x times 1 over x, then y equals 1 over x. And that was what we were trying to prove here, that if xy equals 1, then y equals 1 over x. So that's that. And D. Again, if we use 1 over x in place of x, then we have in C, right? Then we have 1 over x equals 1. And then C tells us that if we have something times y equals 1, then y has to be the inverse of that. So y equals the inverse of 1 over x. Now we know from the inverse property we know that 1 over x times x equals 1. So if we have here that 1 over x times y equals 1, then we know from the inverse property that this has to be the inverse of this. That means that this is y, so that 1 over x times 1 over x equals 1. That means that x has to be 1 over x. So therefore, x equals 1 over x. And that's what we were trying to prove, right? 1 over x equals x. Okay, good.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.